begin with definition 2. Take your copybooks, take your pens, and write down. Definition 2. The point that separates the convex part of a continuous curve from the concave part is called the point of inflection of the curve. Write down the point that separates the convex part of a continuous curve. From the concave part is called the point of inflection of the curve. It's L. The point of inflection of the curve. In this picture, the point O, A, and B are point of inflection. It is obvious that at the point of inflection, the tangent cuts the curve, because on one side the curve lies under the tangent, on the other side above it. Let us now establish the sufficient condition for a given point of a curve to be a point of inflection. Theorem 2. Let a curve be defined by the equation y is f of x. If f2 of a is 0, or f2 of a does not exist, and the derivative f2 of x change sign when passing through x is a, then the point of the curve with abscissa x is a is the point of inflection. proof. The first, let f2 prime of x is greater than 0 for x is maybe begin with negative less than 0 for x is less than any point a, and the second derivative f2 prime of x is greater than 0 for x is greater than L. Is greater than A. Then for x is less than A, the curve is convex up. Maybe write down this. For x is less than A, the curve is convex up. This. And for x is greater than A, our curve is convex down. This. Hence, the point A of the curve with abscissa x is A is the point of inflection. This case you can see in this picture. Here convex up, here convex down. A is point is inflection. The second case. If f2 prime of x is greater than 0 for x is less than b, and f2 prime of x is less than 0 for x is greater than b, then for x is less than b, the curve is convex down. And for x is greater than b, the curve is convex up. Hence, the point in this case B of the curve with abscissa x is B is the point of inflection. The theorem proof. Consider the example. Example 4 from this theme. Find the point of inflection and determine the intervals of convexity and concavity of the curve y is e to the power of minus x squared. It is Gaussian curve. Solution. The first, find the first and second derivatives. Y prime is minus 2x times e to the power of minus x squared. Y2 prime equals 2 times e to the power of minus x squared times 2x squared minus 1. The second derivative exists everywhere. find the values of x for which y2 prime equals 0. We have 2 times e to the power of minus x squared times 2x squared minus 1 equals 0. From this, x first equals minus 1 over square root of 2 and x second equals 1 over square root of 2 without minus. The third, investigate the values obtained. For x is less than minus 1 over square root of 2, we have y2 prime is greater than 0. For x is greater than minus 1 over square root of 2, we have y2 prime is less than 0. The second derivative changing sign when passing through the point x first, hence for x first is minus 1 over square root of 2 there is a point of inflection on the curve. Its coordinates are minus 1 over square root of 2, it is x, and y is e to the power of minus 1 over 2. Then, for x is less than 1 over square root of 2, y2 prime is less than 0. For x is greater than 1 over square root of 2, y2 prime is greater than 0. Thus, there is also a point of inflection of the curve for x 2 equals minus 1 over square root of 2 its coordinates are 1 over square root of 2 e to the power of minus 1 over 2. Incidentally, the existence of second point of inflection follows directly from the symmetry of the curve about the y-axis. The fourth. From the foregoing, it follows that for minus infinity is less than x is less than minus 1 over square root of 2, the curve is concave. For minus 1 over square root of 2, is less than x is less than 1 over square root of 2. The curve is convex. This case. For x from 1 over square root of 2 to plus infinity, the curve is concave. The second. From the expression of the first derivative, y prime equals minus 2x times e to the power of minus x squared. It follows that for x is less than 0, y prime is greater than 0, the function increases. For x is greater than 0, y prime is less than 0, the function decreases. Here increases, here decreases. For x is 0, y prime is 0. At this point, the function has a maximum, namely y equals 1. The foregoing analysis makes it easy to construct a graph of the curve. Here minus 1 over square root of 2. Here 1 over square root of 2. Here 1 is point, and we have this is points of inflection. Next example, example 5. Investigate the following curve for points of inflection. Y is x minus 1 to the power 1 over 3. Okay. Solution. The first. Find the first and second derivatives. Y prime is 1 over 3 times x minus 1 to the power of minus 2 over 3, and y2 prime equals minus 2 over 9 times x minus 1 to the power of minus 5 over 3. It is 1. Okay. The second derivative does not vanish anywhere. But at x as 1 it does not exist. The third. Investigate for value x is 1. For x is less than 1. y2 prime is greater than 0. The curve is concave. For x is greater than 1, y2 prime is less than 0. The curve is convex. Consequently, at x is 1, there is a point of inflection. It will be noted that for x is 1, y prime equals infinity. The curve at this point has a vertical tangent. As you can see, in this picture. Yeah. Y, O, X. This point X is 1. Here vertical tangent. In this we have a way here and now I sent to you the photo of this boat, the screenshot of this boat in the chat. Okay. Wait 1 minute, please. I sent. Do you see? Now I clean the boat, which we continue. Now maybe I check you. I can see in our class Abdallah Youssef, Ahmed Al Said Hasni, then Al Badri Bakir, Tahsin Abd Ali, Daoud Abdurrahman Gamal Ismail Abdulmaneim El-Missiri Ziad Ibrahim Abdul Samad Shaban. Then Mohammed Abdurrahman Said Mohammed, Sagair Hussein Ashraf Hussein, Hassan Mohammed Ashraf Mohammed Ali, and Shenuda Malak Gamal Salam.
Yes, Doctor.
Okay. Other students don't come in our class. Don't sit with you. Yes, I say, and we continue. Our next subtitle, Asymptotes. Asymptotes. Very frequently one has to investigate the shape of a curve y is f of x and consequently the type of variation of the corresponding function in the case of an unlimited increase in absolute value of the abscissa of ordinate of a variable point of the curve or of the abscissa and ordinate simultaneously. An important special case is when the curve under study approaches a given line without want as the variable point of the curve recedes to infinity. Write down definition. The straight line A is called an asymptote to a curve. If the distance delta from the variable point M of the curve to this straight line approaches zero, as the point M recedes to infinity. We can illustrate this definition in these pictures. In future, we shall differentiate between vertical asymptotes parallel to the axis of ordinates and inclined asymptotes not parallel to the axis of ordinates. The first vertical asymptotes. From the definition of asymptote, it follows that if limit as x approaches a plus 0 of f of x equals infinity, or limit as x approaches a minus 0 of f of x is infinity, or limit as x approaches a of f of x is infinity. Then the straight line x is a is an asymptote to the curve y is f of x. And conversely, if the straight line x is a is an asymptote, then one of the foregoing equalities is fulfilled. Consequently, to find vertical asymptote, one has to find values of x is a such that when they are approaches by the function y is f of x, the latter approaches infinity, then the straight line x is a will be a vertical asymptote. For example, consider the example. Example 1. The curve y is 2 over x minus 5 has a vertical asymptote. X is 5. Since y approaches infinity as x approaches 5. This as we can see in this graph. The second example, example 2. The curve y is tangent of x has an infinite number of vertical asymptotes. X is plus or minus pi over 2. X is plus or minus 3 pi over 2. X is plus or minus 5 pi over 2. 2. And so on. This follows from the fact that tangent of x approaches infinity as x approaches the values plus or minus pi over 2 plus or minus 3 pi over 2, etc. We can see it in next figure. In this graph of tangent. The second case. Inclined asymptotes. Let the curve y is f of x have an inclined asymptote whose equation is y equals kx plus b. Formula 1. Determine the number k and the number b. Let m of x, y be a point lying on the curve and n of x, y with the upper line, a point lying on the asymptote. The length of MP from M to P, here length, is equal to the distance from the point M to the asymptote. It is given that limit as x approaches plus infinity of MP equals 0, formula 2. Designating the angle of inclination of the asymptote to the x-axis by phi. We find from triangle NMP that NM equals MP over cosine of phi. Since phi is a constant angle not equal to pi over 2, by virtue of the foregoing equation, limit as x approaches plus infinity of nm equals 0, formula 2 prime maybe, and conversely from 2 prime we get 2. But nm equals modulus of qm minus qn, or modulus of y minus y with the upper line, that equal to modulus of f of x minus kx plus b. And to prime take the form limit as x approaches plus infinity of f of x minus, maybe without bracket, kx minus b equals 0, formula 3. To summarize, if the straight line 1 is an asymptote, then 3 is false. And conversely, if given constant k and b, equation 3 is false, then the straight line y is kx plus b is an asymptote. Let us now define k and b. Taking x outside the brackets in 3, we get limit as x approaches infinity, x times bracket f of x over x minus k minus b over x equals 0. Since x approaches plus infinity, the following equation must be fulfilled. Limit as x approaches infinity of x times this bracket equals 0. For b constant, limit of b over x equals 0. Hence, limit as x approaches plus infinity of f of x over x minus k equals 0 on k equals limit as x approaches infinity of f of x over x. Formula 4. Knowing k, we find b from tree. B will be equal to limit as x approaches infinity f of x minus kx. Formula 5. Thus, if the straight line y is kx plus b is an asymptote, then k and b may be found from 4 and 5. Conversely, if the limit 4 and 5 exist, then 3 is fulfilled and the straight line y is kx plus b is an asymptote. If even one of the limit 4 and of 5 does not exist, then the curve does not have an asymptote. It should be noted that we carried out our investigation and applying to next figure, this figure. As x approaches plus infinity, but all the arguments hold also for the case x approaches minus infinity. Consider the example 4. I'm sorry. Find the asymptotes of the curve y is x squared plus 2x minus 1 over x. Solution. The first, look for vertical asymptote. When x approaches minus 0, y approaches plus infinity. When x approaches plus 0, y approaches minus infinity. Therefore, the straight line x is 0 is a vertical asymptote. The second, look for inclined asymptotes. K equals limit Sx approaches plus or minus infinity, y over x equals limit Sx approaches plus or minus infinity, x squared plus 2x minus 1 over x squared equals limit Sx approaches plus or minus infinity of 1 plus 2 over x minus 1 over x squared approaches 0, 1 over infinity equals 1. That is, k is 1. Find b. b equals limit Sx approaches plus or minus infinity of y minus x, or limit Sx approaches plus or minus infinity of x squared plus 2x minus 1 over x minus x. This limit Sx approaches plus or minus infinity x squared plus 2x minus 1 minus x squared over x here plus equals limit Sx approaches plus or minus infinity of 2 minus 1 over x, here approaches 0, equals 2. Or finally b is 2. Therefore, the straight line y is kx plus b 1x plus 2, or just x plus 2, is an inclined asymptote to a given curve. To investigate the material position of a curve and an asymptote, let us consider the difference of the ordinates of the curve and the asymptote for one and the same values of x. X squared plus 2x minus 1 over x minus x plus 2 equals minus 1 over x. This difference is negative for x is greater than 0 and positive for x is less than 0. And so for x greater than 0, the curve lies below the asymptote, and for x is less than 0, it lies above the asymptote. As we can see in this figure. In this figure. Maybe example 5. Example 5. Find the asymptotes of the curve y is e to the power of minus x times sine of x plus x. Solution. The first, it is obvious that there are no vertical asymptotes. The second, look for inclined asymptotes. K is limit as x approaches infinity of y over x plus infinity. We have 1. B that equal to limit as x approaches plus infinity of y minus k times x equals 0. Hence, straight line y is x is an inclined asymptote as x approaches plus infinity. The given curve has no asymptote as x approaches minus infinity. Indeed, the limit of y over x as x approaches minus infinity does not exist. Now I give you the screenshot of this board in the chat. Clean the board and we continue. Can you see the board in the chat? You can? Do you see?
Yes.
Okay. Now I can clean this board. And we continue. Our next subtitle: General plan for investigating functions and constructing graphs. General plan for investigating functions and constructing graphs. The term investigating of a function usually implies the finding of the the natural domains of the function. The second, the discontinuities of the function. The third, the intervals of increase and decrease of the function. The fourth, the maximum point and the minimum point, and also the maximal and minimal values of the functions. The fifth, the regions of convexity and concavity of the graph and point of inflection. The sixth, the asymptotes of the graph of the function. The graph of the function is constructed on the basis of such an investigation. It is sometimes wise to plot elements of the graph in the very process of investigation. If the function under investigation y is f of x is even, that is, such that upon change of sign of the argument the values of the function does not change, then it is sufficient to investigate the function and construct its graph for positive values of the argument that lie within the domain of definition of the function. For negative values of the argument, the graph of the function is constructed on the grounds that the graph of an even function is symmetric about the ordinate axis. If the function y is f of x is odd, that is such for any change in the argument the function change sign, then it is sufficient to investigate this function in the case of positive values of the argument. The graph of an odd function is symmetric about the origin. Since a knowledge of certain properties of a function allows us to judge of the other properties, it is sometimes advisable to choose the order of investigation on the basis of the specific peculiarities of the given function. For example, if we have found out that the given function is continuous and differentiable, and if we have found the maximum point and the minimum point of the function, we have thus already determined also the range of increase and decrease of the function. In next class, we will investigate curve represented parametrically and consider the examples of investigating the curves. Now we must end our class because our time is end. Now I create your homework and you must send to me in this program your writing, your today's writing, as we do it everywhere. Goodbye, good luck. I record this lecture because you can see this lecture in my YouTube channel. Goodbye, good luck.
Bye.
I wait for you on our next class.